Okay, currently a lot of things happen. So for those who are interested in observing astronomy a bit, there is an event that will happen next Wednesday, so actually during our class, which is the transit of Venus across the Sun, or something like that. We'll have the Sun and the Venus will transit through it. It's barely visible with by naked eye. We try to do that. It's a very small dot. Of course, Venus is very small compared to the Sun. And as I mentioned a couple of weeks ago, the Sun is very active currently, so there are lots of sunspots. So it would be difficult to spot by our eye, but I don't have time to set up apertures. But this Saturday we'll collect some shades from the Astronomical Museum, and during the break next Wednesday we'll try to spot it by eye. So it's just here, this figure showing where you can see the whole transit. And this place here, so in the Pacific Ocean, it's where you would see the entire transit. So in Taiwan, we are one of the rare places in the world where we'll be able to see that completely. So it starts at 6 o'clock in the morning, but the peak, the maximum of transit, that means when the Venus will be at the center here, will happen at 9:30 during the class. So we'll go out and have a look at it quickly. Remember, and this actually quite relevant with what we're going to discuss today, because today we're going to talk about exoplanets. That means planets that are orbiting other stars, and we'll discuss about methods to detect them. And one of the methods is called the transit method. That means that you observe a star for a very long time, and if there is a planet going in front of it, then the light of the star will be a bit dimmer. In the case of the transit of Venus, it's 3%. So you have a decrease of the flux of the Sun by 3% if you look at it. And the total duration of the transit is around 6 hours. So it gives us plenty of time to look at it. Once again, like for the eclipse, don't look at directly with the eyes. Please use shades, because otherwise you go blind. And don't blame me. And something that you have to know is that the cycle of the transit of Venus, it's something that happened quite rarely. It's a cycle of 8 years, so it happened once, 8 years after it happened again. Then you have to wait for 105.5 years. Then you have another transit, then 8 years again, another transit, and then you have to wait for 121.5 years for it to happen again. So this one happened in 2004, so we're in 2012. So if we miss this one, well, you won't see it. So we'll try to have a look at it. Shouldn't take too long. It depends also on the weather. If it's cloudy, then we stay in the room. The past 3 weeks, we have been working on the characteristic of stars. And last week, I explained to you how stars are formed and how they are evolving. And so lots of physics in there. I recognize that it's a complex thing and difficult lecture last week. This week will be slightly easier. This week we're going to discuss about the quest of planets orbiting other stars. It's called exoplanets. So it's a very interesting question. Obviously, is there life anywhere else in the universe? We can do that by exploring the solar system. We discussed about it a little bit during the lecture on the solar system, looking for water or looking for liquid water mainly and source of energy, like on the icy moons of Jupiter or on Mars. Now we are going a bit further. Remember, there are billions of stars in our Milky Way, and there are billions of galaxies similar to our Milky Way. So that's a lot of stars in the universe. And so far we only know one star around which orbit a habitable planet, which is Earth. But there are so many other stars, so the chances that we get another planet like Earth orbiting another star is quite high, because there's so many of them. So that's what we are doing today. And the question is how we can spot them, how we can detect them. So, just a brief reminder about our own solar system, because what we are trying to look for is something that is similar to our own solar system, and we pretty well know our own solar system. So first of all, remember that our star is just a G2 star, so G25 actually, remember? Main sequence G2 star, it's actually not a very rare star, and many like them. It's not the more numerous. The more numerous are cooler, but still, it's quite a common star. And around this star, we have terrestrial planets and Jovian planets, remember? And we have also gaps, for instance, between Mars and Jupiter, where we find dwarf planets. And at the outskirts, we have what we call the Kuiper belt, with all those asteroids. And we have discussed about possible scenario of them. So remember, we saw that the definition of planets, the difference between a planet and a dwarf planet. So a planet has to orbit around its sun or around a star. It needs to have sufficient mass to be round shape. So we suppose that they are big enough to be round to differentiate them from asteroids. And something very important, it has cleared the neighborhood around its orbit. That means that there is no residual belt of asteroid in the same orbit than the planet. And this is the main difference with dwarf planets. Dwarf planets, remember, they are not satellite. They can't be satellite. But the condition A and B are the same. But in the case of dwarf planets, it's still in a very crowded orbit. So we can take the example of Ceres between Mars and Jupiter, which is in the asteroid belt, or Pluto, which is in the Kuiper belt. And all the other objects were called small solar system bodies. We already have discussed about that. So we have the Sun, our 8 planets, Mercury, Venus, Earth, Mars, that are rocky planets, telluric planets, and Jupiter, Saturn, Uranus, and Neptune, that are giant planets. And then we have those dwarf planets like Ceres, Pluto, 2003 UB 313, and so on. Many of them. We have discussed about that already. So just briefly, remember, terrestrial planets are small, dense, and rocky. They barely have moons, and they don't have rings, and they are very close to the parent star. And gaseous outer planets are large gases. There are lots of moons, they have rings, and usually they are far away. Okay, I will jump on that. Remember the top view of the solar system. The sun is at the center. Then up to Jupiter, which is here, things are pretty close one to the other. You have the asteroid belt here, and then the giant gaseous planets are far away, and you have those dwarf planets that are not in ecliptic plane. And we mentioned that last week as well. There is a very fuzzy limit between what is a star and what is a planet, in fact. Remember, I told you several times, Jupiter is considered as a faint star. And I mentioned several times as well that we have lots of examples. Almost 50% of the stars we see around there are actually in binary systems. So they are having 2 stars together. So the difference between a planet like Jupiter and a star like a brown dwarf that we mentioned. So brown dwarfs are very red, very cool stars that are living for very long time and are very small. This difference here is very fuzzy. We can have, and we still don't really understand what's happening exactly between those two. So the physics that happens in brown stars is slightly different than happens in the sun. I mentioned that last week. So how do we find extrasolar planets? Well, first, what are extrasolar planets? So they are planets that are orbiting a star other than our sun. Right? And why bother? Well, the mainstream idea is to look for life, or to look for a planet that is similar from Earth. Are we really alone in the universe? So this is the question that we sell to journalists. But what interests actually astronomers is more the second question, is how our solar system was formed. Okay? Search for life is an interesting question. Astrobiology is working on it, but we're pretty sure that we won't be able to answer to it in the nearby future. But this question of the formation of a solar system is actually a crucial one for understanding of the formation of stars and formation of planets in general. So by looking at other systems that are our own systems, we can learn a great deal of things about formation of solar systems. You remember I insisted it since the first lecture. In astronomy, we're doing usually study one particular case in very high detail because it's easy, the example of Earth or the example of the Sun, or this case, the example of our solar system. But we want also to generalize what we learn from close-by system to general characteristics of further objects like stars in general, planets in general, and solar systems in general. So by detecting extrasolar planets and studying their system, we can learn a lot about our own system as well. So what do we expect to find? Well, if our solar system is typical, that means that if our scenario formation is really working very well, then we expect to find copies of our solar system. Lots of planets around a single star, inner planets, rocky planets inside, giant planets outskirts. However, if our solar system is special, it's not like the others, then we will find other solar systems that are very different. And in that case, maybe there are problems with our scenario of formation of solar systems. But this is a difficult problem because we have a bias, actually. The bias in the sense that big planets are heavy planets are easiest to find. And we saw in the different techniques to detect extrasolar planets that actually it's easier to find the big planets. So we expect that the first planets we will find will be big and gaseous. And when the techniques getting refined and our technology is getting better, we expect to find the small rocky ones. It's easier. It's always easier to find the elephant than the ants, right? So we expect to have a bias. We expect to find actually gaseous planet first. However, we can learn a great deal of things about just looking at other Jupiters around other stars. So it's not totally true. Nowadays, we already have detected a couple of rocky planets, or very few of them. So how do you search for planets? Well, first, it's extremely difficult. Understand that the star is a billion times brighter than the reflected light. So for instance, we look at the moon. The albedo on the moon looks very, very bright to us during the nights, but it's because the moon is very close to us. But from a faraway distance, the moon will barely be visible. The light reflected by any body in the solar system is very small compared to the light emitted by the sun itself. So it's exactly like trying to distinguish a grain of sand nearby a very bright light bulb. You will be blind by the grain of sand, by the light bulb. You will never be able to detect the object. So it's very difficult. And usually planets they are too dim. They don't emit enough light, reflect enough light, and usually they are very close. If they were far away, you could be able to resolve it. But usually they're very close, so it's very difficult to resolve the problem. So we have to use indirect observation. You already know some of them, and I'm pretty sure that it will ring some bells. So what you want to look at is the effects of the presence of the planet on the light coming from the parent star. So it's indirect method. You won't be able to see the planet itself, but you will be able to see the influence on the planet on the star. It could be gravitational. Remember the story of Uranus and Neptune, how they were discovered. Or it could be things like Doppler effects, for instance. So, direct observations can't work with stars. I'll show you in a second why. It works very well for double stars, but it won't work for planets coupled with a star. And what we can do is observe gravitational wiggles through Doppler effect. Actually, the presence of the planets will make the star moving a bit, because the center of mass won't be exactly the center of the star. So we will have a Doppler effect when the star is getting redder and bluer periodically. This is one way. Or the transit that I just mentioned about Venus. If you have a planet going in front of the star, then you will have part of the light that will be blocked. It's kind of an eclipse. So you can look at it through a dimming of brightness curves. Okay, so we're now going to detail all those different methods. So what happened? Why can't we really do direct observations? If members of a system are well separated and distinguishable, then you should be able to observe the different system like this. So this is the case of a double star here. So you have the biggest star around there, and this is how the double star has been placed since 48, 55, 60, 65, 70, 75. So you can see the parent star, the biggest star here, and the smallest star turning around it. So directly we can do that. But you need to have two objects that are far away enough. and both to be bright enough for you to be able to see it. Problem is, with stars, with planets, it won't work. You won't be able to see that kind of things directly. So it just can't, it's just not possible. So what we can use is the trick of the virtual orbits. Remember, we have seen several times this problem. If you have a star, a double body system with a star and a planet, then the center of mass of the system is slightly shifted away from the center of the star. So what you will have is the star will turn around the center of mass, and the planet will turn around the center of mass. Something like that. Okay? The center of mass of the star will be shifted, and so you will see actually the star oscillating. So you can do it actually by measuring very precisely the position of the star, of the center of the star. So it's called astrometric techniques. So what the idea is you look at a very, very, so this is very, very small. It's 0.002 arcsecond of the sky. Remember, it's very, very, very small angle. And here, this is where the center of the star is in 1990. And you look at where it is in 1995, 2000, 2005, 2010, 2015, 2020. And so you will see the center of the star actually moving around its original point. This is probably due to this kind of system, this kind of problem we see here. Okay? Back. Right? So if you look at the center of the star, you will see it wiggle around the center of the mass system. The problem is, you not always look face on. Sometimes it can be inclined. That explains why we have those very weird patterns. If it's not exactly face on, it won't be circular. It will start to do weird motions. So this is a simulation, actually, of the motion of the sun as viewed from a star 30 light years away from us. So this is how the motion of the sun will look like with all the planets around it. So the center of mass of the sun, of the system, our solar system, is quite chaotic. It's quite a bit weird. So this distance here, to give you an idea, is the angular size. Remember the size on the sky of a standard newspaper font from 300 kilometers away. So I take this one letter here. I put it 300 kilometers away from you, and this is the kind of resolution we need to achieve to be able to see that. It's not impossible. We start to have techniques to do that, but it's extremely challenging and difficult. And here, it's only 30 light years away from us. The main part of the stars are far away from that. So it's unobservable, basically. So not impossible, it's extremely difficult to do. So it will work for very close objects, but in general, we can't do it. So we need to find other methods. We can't do it directly. But the idea is there. The center of mass of your star will move around. So we can use other techniques. And the other techniques, we are back to the Doppler shift again. We have seen that several times. So what you will see, you will never be able to detect the planet, but just by observing the star and seeing the star, in motion of the star will vary around this center of mass. So what you will observe is when the star is moving towards you, the lights will go bluer, and the star will move away from you, the lights will go redder. So another example of how we can use Doppler shift. So remember, if you have this star and this planet, you can't see the planet, but what you can look is observe the star. And on the line of sight, what will happen is here, in that case, the star will look like it's moving away from us, so it will be redshifted, in this case. And in that case, it looks like the star is going blue towards us, so it will look blue shifted. Okay, blue shifted, red shifted, red and blue. And so far, the large majority of the stars, the planets around other stars, have been detected this way, using this technique. So what you will see is you look at the velocity of the star on the line of sight. That's what we call radial velocity. You look at the star on your line of sight, and you see when the star is coming up and back. So here it's when it's getting redder, so it's moving away from us, and here it's going bluer, it's going towards us. And so you monitor the star for many years, in that case 10 years, and you will see all these points are measurements, and all what you will see is that actually the star is doing a rotation around the center of mass. So from that, we can derive the mass of the planet. Remember that there is always the projection effect. This is when the thin eye is coming. We mentioned that last week. The Doppler shift works only if you look at the system, at least on the edge. So this is the star and this is the planet. So you look on the edge of it. If you look face on, you won't see the Doppler shift. But in the main part of the cases, the problem is not exactly face on and not exactly on the edge. It's inclined. And this angle between being face on and being inclined is called I. So you take the sinus I, and the mass of your planet detected by this method, you won't be able to distinguish the mass from the projection angle. So for this particular case, this particular planet, the M sinus I of this planet is 0.6 times the mass of Jupiter. 60% of the mass of Jupiter. Once again, this technique is very efficient, and so far the main part of the exoplanets detected have been detected using this method. And the other very popular method is the method of transits, exactly like we will see next week with Venus. So here you have your star, and you have the planet that is going in front of it. So the planet will eclipse the star at some point. The planet will be between us and the star during one of its periods. So this is the sketch of what will happen, is that you have your star emitting light, because the planet usually will be smaller than that. So in position 1, you have all the light coming from the star. So this is brightness, how bright the star is, and this is time. So in position 1, you have all the light coming here. Then the eclipse starts to happen. So you have an increasing fraction of the light of the star that is obscured by the presence of the planet on the line of sight. So from 1 is decreasing to reach this step 3, where the planet is in the disk of the star. And then when the planet is moving away from the disk of the star, then you come back to the normal brightness of the star. So this very small deepen, the very small hole in the light curve, will depend on the relative size of the planet and the star. You understand that if the star is smaller and the planet is bigger, then this thing will be deeper. So usually it's extremely small, but it's actually working very well. And this is a good example because this is an exoplanet discovered by amateur astronomer, non-professional. So the guy had a 0.4 centimeter telescope in his garden with a CCD camera and observed a star for a very long time. This is time, and this is the differential magnitudes. And what you've discovered is the depth of it here. So it has been done by a non-professional. So if you have lots of time and being very careful and detailed, anyone can detect exoplanet using this kind of methods. So here you see the depth very easily, and you can derive the relative mass, the relative size and relative mass of the planet compared to the star. So these are the two main methods, and actually the most popular and the most efficient. There are several other that I won't describe too much, but we can mention. One is the spectroscopic method. Is if you look at, you have the star here and the planet here, okay, and you're here, and by chance the planet has an atmosphere, for instance. Light of the star will go through the atmosphere and come to your eye. So that means that, and of course the star is orbiting, the planet is orbiting around the star. That means that from time to time you will see appearing other lines, absorption lines in the spectrum that are not there the main part of the time. Every time the planet will come in front of the star in your spectrum, you will see absorption lines that are not there the main part of the time. And those absorption lines correspond to the composition of the atmosphere. This could work theoretically. In practice, it's very difficult because the absorption line will be very weak. So it's very difficult to detect. And it will happen for a very narrow period of time. But this is one of the techniques to look for instance, this is the only technique actually, to look for planets with atmospheres. Gravitational lensing is a bit complex idea, but the idea is the presence of the planet, it will actually deform a bit the size of the star. Sorry. So this is a gravitational effect known since Einstein. I don't have time to explain too much about it, but remember when we discussed about black holes last week, I told you like if I have a field of star and I put a black hole at the center here, all my star will actually move away and be a bit deformed due to the presence of the black hole at the center. So stars won't be here anymore, and they will move and be a bit deformed away from that. So this is because the black hole is bending light on the line of sight. So this is quite a complex phenomena, but we observe it actually very well with galaxies and cluster of galaxies. So people are thinking that we may have similar ways of detecting exoplanets using this method. So far, none of the planets have been detected this way because it's very weak effect and probably it will be almost impossible. The last method is also a very rare case. So all those cases are very rare. It's not really common for detecting planets. If you have, for instance, a star that has a very thick disk of dust, so it's a very young star. Imagine you take stars at the early stage of the formation of the solar system. So planets are not completely formed yet, and you have lots of dust, asteroids in the disk. Remember the first stages of the formation of a solar system. Then if you have a planet like a Jupiter planet that will start forming, you will see some disturbance, you will see some resonance in the disk of dust. And that will give you a hint that there is a planet in formation around there. Exactly like we have holes in the rings of Saturn. Okay? But this works only for very young stars. I updated the numbers here. So if you're really interested in that, you can go to this web page, Observatoire de Paris in France, and they have a catalog updated every time someone detects an exoplanet. So far, 5 days ago, there were 770 planets discovered around other systems. 477 were detected using these wiggle methods, or by astrometry, or by Doppler, the main part of them by Doppler. 231 by transit, that means the absorption, and 62 by using other methods. And among those 770 planets, we have 102 multi-planet systems. That means systems where we have more than 2 planets in it. The first exoplanets actually have been discovered in 1991, but it was around a very peculiar kind of star, neutron star. So you remember those very, very small, extremely dense objects. But the first extrasolar planet detected around the normal star was discovered in 1995. And it's called 51 PEG. So it has been discovered by Michel Mayer and Didier Queloz in the Observatory of Geneva in Switzerland, from the Observatory of Geneva in Switzerland, and they use a telescope in south of France, Observatoire de Haute-Provence. Actually, I did my PhD over there, but I was not there yet when they did the discovery. It's a very nice place. It's the middle of Provence. Anyway, and it is orbiting. So this extrasolar planet is orbiting a star called 51 Pegasi. So you look at the constellation of Pegasus, and 51 Pegasi is here. It's half of the mass of Jupiter, and it has been detected using the Doppler shift method. It orbits its star in 4.2 days, compared to 4,350 days of Jupiter. And it's 5 million miles from its star. That means it's 1/8 of the distance Mercury-Sun. So this planet is orbiting a star, which is quite similar to our Sun. The planet is half of the mass of Jupiter, but it's 1/8 of the distance Mercury-Sun. So we already have a problem. The first planet we detected doesn't fit at all with any of the scenario I discussed about a few weeks ago. It's a giant gaseous planet that is closer to the Sun than Mercury. And you remember, according to the scenario, we can't have that because we can't have hydrogen. so close to the sun in the formation of the solar system. If the scenario I discussed about a couple of weeks ago is true, then this kind of planet, gaseous planet, should have been formed far away, at almost the distance of Jupiter. However, this one is there, extremely close to its sun. So there is a problem here. First exoplanet discovered, it put lots of questions in our understanding of the system of formation of solar systems. That was a good discovery. When you discover something, it's exactly like we are predicting, it's boring. When it's really not at all that way we were expecting, that's very interesting. So far, I told you we have now 770 planets discovered, and they are everywhere. You can look. This is the map of the sky with a different constellation, and here it's pointing an example of different planets where they were discovered. So they are everywhere. There's no particular place where we can find them. We just have to observe as many stars as possible. And they are very diverse. But if you look at the first one that have been discovered, so this is the orbital semi-major axis of the star, the planet around its star. So here, this is where Earth is, okay? And here it's twice Earth. Jupiter should be around there. And these are ranked from distance to there. So Mars is here, okay? So Jupiter is very far away from here. And here they are ranked in the distance compared to their central star. So 51 peg is here. And this indicates the mass compared to the mass of Jupiter. So this one is 4 times the mass of Jupiter. And it's extremely close to its parent star. This one is 10 times the mass of Jupiter. It's still closer than Earth. It's around between Mercury and Venus. And then you can discover things that are 4 times the mass of Jupiter, but still it's far too close from its parent star. So the main part of the exoplanet detected at the start were what we call hot Jupiters. I mean, Jupiter-like planets very close to their star. And it's a problem. We come back on that. We had to really change our views on formation of solar systems. But I want to stop a second here and I try to make you understand that this is actually expected. Because of the method that we are using, we expect to detect, I mentioned to you, big planets because they are easier to detect, and we detect them indirectly. So actually, we detect planets through the gravitational interaction of the planets on its star. The presence of the planet makes the star wiggle a bit. So if your planet is very small, the wiggle would be so small that we won't be able to detect it. So in order for us to detect it, the planet needs to be big. Okay? And the same reason, if the planet is very far away, the effect on the wiggle on the star will be very weak. But if the planet is very close, then you will see it very well. So by the way we observe it, using or the transit or the wiggle method, for the transit the same thing. If the planet is big, so that means large and close, the eclipse will be stronger. If the planet is small and far, the eclipse phenomena will be very weak, so you won't be able to detect it. So it's what we call an observational bias. It's because of the techniques we're using, we are unable to detect small planets far away from their parent star. The other way around, because of the techniques we're using, we are meant to detect big planets close to their stars. So we shouldn't worry too much. Those objects may be actually very rare, but it's because they are easy to detect that we see them. But when, and it's starting to be more and more the case actually, when our techniques are improving, then we start to be able to detect smaller planets more distant. Actually, so far, I think we have discovered 2 telluric planets. So super Earth planet, 2 or 3 times bigger than Earth. So remember that. Among those 770 planets discovered so far, maybe 750 are very weird. But it's because of the technique we're using to detect them. So we don't worry too much about it. However, we need to explain why they exist. Okay, in some cases we can also discover multiple systems. So for instance here This is a star, so well, it's because of the technique, it's an interferometric technique to detect it, but we can now have more or less direct ideas or imaging of it. This is one of the rare cases where we can do direct imaging. So the star here is quite close to us, and using imaging techniques, we'll be able to see directly those 3 planets. So the star is around there, and we have 3 planets here, B, C, D. So for instance, we have several systems, multiple systems that have been detected in the past 20 years. 20 years. So this is an example of Eta and Andromeda. So this is a system with 3 planets. It's a system with 3 planets, and they are all actually Jupiter-sized planets. So 75%, twice and 4 times. And this is as a comparison with our solar system. And we almost detected one system that is very similar to ours. It's called 55 Cancri. So the star is 60% as bright as our sun. So this is our solar system with the sun here, Earth and Jupiter. And this is 55 Cancri system. So the star is 60% as bright as the sun. It's 5% less massive than our sun. And there are 4 planets orbiting it. The outermost planet has an orbit similar to the orbit of Jupiter, and it's 4 times bigger. So that was the good news. At least we can find some planets that are similar to Jupiter now. But the 3 inner planets are within the orbit of Mercury, and they're all, and one of them is as big as Jupiter. So it's not exactly our system. But we start to be able to detect actually Jupiter size at where Jupiter's orbit is compared to the Sun. So a brief summary about it. The most parts of the planets discovered so far are Jupiter-sized. It's not a surprise because those more massive planets cause their parent stars to move more, so therefore they are easier to find. So you really have to understand that. That's not a worry. That's a bit normal. By bias, we know that we detect this kind of planets. And usually they're closer to their parent star. We'll see that in a minute after the break. They are mainly non-circular. Actually, they have very elongated orbits. Well, remember, the main part of the star in the solar system are orbiting around the sun with almost circular orbit, apart from the dwarf planets. Those ones usually have very elongated orbits that give us hints of of their formation and evolution. And on the 14th of May 2010, but it evolved since, we have now detected several of them, what we call super Earth, the telluric planets 2 times the mass of the Earth. So the estimation currently is that we have at least 20 billion of planetary systems in our galaxy. And one of them, Gliese 581, is a terrestrial planet in the habitable zone. And what are the implications on the scenario formation of the solar systems? So once again, I want to insist once again on that, is the fact that we detect these very weird kind of planets is not a surprise. This is something that, given the method we're using, was expected. It's not completely crazy. However, so what that means is that probably our scenario still work, but we need to find ways to explain those slight differences. Remember, in our own solar system, the scenario is telling you that everything is forming in motion. So that's why all the planets in the solar systems are turning in the same direction. All the planets are formed by accretion systems. So, for instance, of gas in the outer part and rocks in the inner part. So all the planets are turning on the orbit in the same way they're turning around the sun. So this is the theory. In practice, we know several examples, like Venus or Uranus, for which it's not the case. Venus is a retrograde, is turning the other direction away than the rotation around the sun. So instead of turning like that, it's turning like that. So the other way than the others. And Uranus' orbit is not perpendicular to the rotation, it's actually in the disk, in the plane. And if you remember what I was saying during the lecture about the solar system, is that one way to explain that is because of interactions. So what could have happened is that an object will hit those different planets and make their motion different than it should be. So we came up now with this kind of ideas a bit later. But first, let's come back on the scenario of formation of the solar system. So first, planets are far apart. They are not bunched together. We have planets are regularly placed in the solar system. They are not all compact in one particular locations. And what we know about our own solar system is the orbits of planets in general is nearly circular, maybe slightly ellipsoidal, but it's mainly circular. The orbits of the planets lie mostly in a single plane. Exceptions are dwarf planets, but we remember dwarf planets are not planets, so they probably form in the different time and different ways. But if you look at the 8 main planets in our solar system, they are all within 5 degrees compared to the ecliptic plane. The direction of the revolutions of planets around the sun is the same, I just mentioned that, and the same as the direction of the sun's rotation. So everything is turning around the sun is turning in one way, all the planets are turning in the same way, and all individual planets are turning on their axis the same way as well. This is true apart from a couple of exceptions. So Venus, Uranus, and Pluto. Same thing with the moons, actually. Most moons revolve around their planet in the same direction as the rotation of the planets. And remember that we have differentiation between inner and outer planets, and the way we explained that was the so-called evaporations. The fact that in the proto-solar system, the sun started to get hotter and hotter, and the light elements were pushed away from the central part. While by sinking, the most heavy elements have tendency to go within the central part. So we end up with things that are rocky at the center and gaseous at the outskirts. And we had also to explain the existence of properties of asteroids and comets. Remember, comets are mainly icy. They form mainly from water, and they are usually coming from very far away from the solar system, while asteroids are mainly rocky, and they are the main part of them, in 80%, within the orbit of Jupiter. So all those things are going in the same direction. So remember, if you look at the distribution of temperature compared to the sun to the distance, so this is where the sun is, so Earth is around there at 1 astronomical unit. Then you have Jupiter, Saturn, and Uranus. And the metals are condensated, are more dense at very high temperature around where the Earth is, while water, ice, and ammonia are actually more dense where the temperature is away from us. So this came up down to this scenario that we had a look, we described in details a few weeks ago, where we have first this cloud of gas and dust that is condensated. Because of differential rotation, it will collapse, and conservation of the momentum angulum, it will collapse and form a disk. At the center of the disk, things will get more dense and more dense and more dense, and eventually nuclear reaction will start and the star will light up. Then the temperature at the center will rise, and you will have a phase of evaporation, while all things like volatile elements like water and hydrogen will have tendency to move away, evaporate away from the center of the nebulae, and the more rocky and metal will have tendency to sink towards the center. And you end up with 2 kinds of planets formed. In the center, the small rocks, dust, and grains will start to aggregate to form asteroids, and that collide together because there are lots of them at the center, so they will collide together to form bigger and bigger planetesimals that will end up creating planets. While at the outskirts, you will start to have condensation of those rocky elements. They will create an overdensity, and all the gas will start collapsing on those overdensities and forming gaseous planets. And eventually, if the amount of mass gathered by one of those planets is getting bigger and bigger and bigger, this planet may be transformed into a star itself, and then you will have a binary system. So we end up with this kind of scenario of formation of the solar system that explains very well why all the planets are in the same plan, while they're all rotating, they're all following the rotation of the disk from the start. So they're all rotating around the same way, they're all rotating on the same axis, and all rotating on the same direction than the sun is rotating on its own axis. To explain the differences, then we can call those impact or interactions between planets and asteroids or planetesimals that will knock down the planet and make it behave slightly differently than the others. So this scenario works pretty well. It's a viable theory. And we even have evidences of planetary nebulae nowadays. We have observed these stages directly. However, once again, there's no extrasolar system similar to ours so far. Extrasolar planets do not agree with our theory. And what I said is, it's not a surprise, it's because the way we observe them. So what we think is that this scenario is fundamentally correct, but we need to implement some revisions to explain why few extrasolar planets are actually not behaving the way we are thinking. And it's all coming down again to this story of cleaning up the solar system. Remember that at the start, you don't have big planets, you just have plenty of asteroids all around the place, and some of them are ejected away from the center part, okay, toward the Oort cloud or toward the Kuiper belt, and some of them are just included in the planets in the center. And with time going, while you have asteroids everywhere in the solar system, with time you end up with all asteroids away from it, or in a very peculiar location, like the asteroid belts. And essentially, all the solar system is cleaned out from all those asteroids in 99%. So the small objects are forced out of the inner solar system by gravitational pull of bigger planets. And some of them are actually collide and join the planet system by itself. So how could we explain the formation of other systems? The current model of planet formation predicts that Jovian planets are formed only far away from their stars, while planets should form more often around stars with lots of metal and rocks. And the kind of exoplanets we're finding are mostly big Jupiters with two kinds of orbits. Or they are highly eccentric or close to the star, or they are actually in circular orbits and more typically spacing. What I mean by that is if you look at the number of planets versus semi-major axis, their distance compared to their sun. So this is an example for the 167 first planet discovered. This is where Mercury is, and this is where Earth is, this is where Jupiter is. And you see that the main part of them are actually around the orbit of Earth, and some of them are even closer than Mercury. This is in log, okay? 0, 1, 10. So those hot Jupiters are very big and close to the Earth stars. And if we do another exercise, we just plot their orbit as compared to their relative sun. So, for instance, in blue line, dashed line here, you have the orbit of Earth compared to the sun. So what we do is we take many different planets and we put their star at the centers, 0, 0. Well, this is the distance compared to the center in this direction, and the distance compared to the center in this direction. So Earth here are a very circular orbit, but if you look at all those extrasolar planets, you see that actually it's almost non-circular. The main part of them, even especially at the center, they are extremely ellipsoidal. And when you go to the more distant ones, they start to be a bit more circular. So it tells us that something happened to those stars here. And our best hint is that they were not formed there, they were pushed there. So this is the eccentricity versus the semi-axis major. And you see that of course, the planets that are very close to the star, the orbit is almost circular, almost equal to 0. But for the others, the orbit can be very eccentric. This is one. This is almost on the line. These ones are just orbiting almost on the line. So what happened? Well, we already mentioned this story, actually, when we were talking about the ring system around Saturn. This is what we call the resonance issue. it seems that our system is actually very stable. We are living in a very peculiar place. So if you remember since the start of this series of lecture, the chances to find a planet like Earth, which is habitable, is getting dimmer and dimmer and dimmer. We need to be on a rocky planet at the right distance from the sun, otherwise it would be too hot or too cold. We need to have a big moon to shield us. We need to have geological activity to create magnetic fields to protect us from bad solar winds. And now we realize that we need to be a solar system that is very stable, because what happened in the solar system is that Jupiter kicked in the solar system, so destroying everything that was in inner part of it. So it's getting more and more clear that our solar system is a very peculiar one, and our planet is a very peculiar place. So what we have in our solar system is very, very stable. Things seem very, very ordered. And actually the planet's orbit is very stable. They're not wiggling too much. Because there are so many gravitational effects there. Remember when we discussed about the discovery of Neptune, the discovery of Neptune was coming from the fact that we saw gravitational differences in the orbit of Uranus. So the presence of planets close one to the other makes the orbit of the planet a bit unstable. Instead of turning in very, very stable position, it starts wiggling a bit. And if the wiggles start to be very, very strong, then the planet is just kicked out of its orbit. So that's probably what happened with those big hot Jupiters. So in our solar system, the heavy planets are far out and the lighter planets are closer. So and remember that the force of gravity grows with mass and decreases with distance. So there is no accident. This is not an accident. If they weren't like this, the big planets would gravitationally bully the other around. Imagine that Jupiter's orbit starts to be very unstable and Jupiter falls down within the solar system. Jupiter is 1,000 times bigger than Earth. So Earth would be just kicked out of its orbit very early. And then we end up with a big Jupiter very close to the star with no other planets in the system because they were just kicked away. On the other hand as well, the fact that they're falling in the inner part make their orbit very eccentric. So they are not on a very, very circular motion around their parent star. Eventually they will be kicked out of the solar system completely. So we came up with this idea where actually those very massive Jupiter were formed where they expect to be formed, but due to some gravitational instabilities, they left their orbit and fall closer toward their star, parent star. In the same way, they kicked out any rocky planets that was at the center. And if it happened very early, we didn't have time for those planets to be formed at all. So this is now a distribution of mass of the 167 first planets discovered. So this is a number and their mass. Remember, there is this orientation factor. The fact that when any method we're using, actually the orientation can't be distinguished from the mass. But this is MC9 in mass of Jupiter. So this is the size of Jupiter here, 1, twice, 4 times, 10 times, etc. And this is the distribution of mass of those 170 planets. And you see that actually it's increasing exponentially when you go towards very small masses. So there definitely are more planets in smaller mass range. We have the hints of it. It's just very difficult to detect. So we came up with this slightly modified picture. We actually don't fundamentally change our views of the formation of solar systems, but we just had the fact that we need the system to be very stable to remain the way it is in the way our solar system is. And actually those gravitational instability may be quite common. So we may have a lot of the system in reality being hot Jupiters and very few of them remaining stable. However, the idea is the formation of a solar system is not necessarily the final word on the appearance of the system. Systems may evolve. First, because remember, the star will evolve. The star, for instance, our sun will grow bigger and actually it will almost reach the orbit of Mercury. So will create a lot of instability within the solar system. So things will probably move around when the star will evolve. But even so, before that, you may have impacts that will kick out a planet from its own orbit, for instance. So we have what we call collisions or cleanups. The fact that bigger planets will kick out smaller planets out of their orbits, and those phenomena of migration. When I mentioned that big, massive planets are shifted out of their orbit, and they will fall down towards the inner part of the solar system. So actually, the thing is, how a planetary system looks like today, determined by how it was formed, sure, and what happened in its history. And the same thing that for human beings, right? Genetics is not all of it. We have our history, and when you grow older, your history starts to look on your physical appearance as well. People that have worked very hard in very harsh conditions, they were more marked with life than people that never left the office. And we are quite in a lucky place because it seems that our solar system has been somehow protected from the drama. And we think that it's coming from actually a combination of different things. But the very hierarchical, the fact that we have so many planets, for instance, the fact that the mass of the bigger planets is spread across 4 planets and not concentrated into one. If we had one Jupiter with combining the mass of Jupiter, Saturn, Uranus, and Neptune, maybe things would have been different. So we have been quite lucky to have the mass well spread throughout the solar system, how it has been during its formation. So what's next? Well, the goal now is really to look for Earth-like planets. So try to detect planets at the mass or below the mass of our Earth. And there are many, many experiments that have been set up in the past 20 years, actually, to do that. And some of them are now giving us results. So for instance, Kepler and Corot. So Corot is observing now. Kepler will be launched soon. The idea is to look for a brightness change of stars. So these 2 telescopes are using what we call the transit method. So I think this is Kepler here, and this is Corot here. This is a sketch, of course. So Kepler will monitor 100,000 stars for 4 years. So look always at the same star for 4 years. Okay. So they always monitor 100,000 stars for 4 years and look for dim, periodic dim, to detect exoplanets. Corot, a bit less, but Corot start to give some results now. So among the 770 planets, I think something like 80 has been discovered by Corot in the past year. And we have 2 other experiments in the future, called one very important one called Gaia. So Gaia will monitor billions of stars, and actually it's it's an astrometric experiment. That means that it will have very precise measurements of where the star is and look for its motions. So if the star is moving. So this is one of the methods to look for things that are moving around. So we can learn a lot of things. The main part of the result from Gaia will be the understanding of the motion within the Milky Way, our own galaxy. Discuss about that next week. But one thing that you can do as well is look for the slightly wiggle of positions due to the presence of a planet around it. So we expect to have lots of planets discovered thanks to Gaia. And SIM will do the similar, is a plan for doing the similar things. And then we have TPF and Darwin that are designed for direct detection of planets. So the idea is to really, they have very, very high angular resolution. So I told you 0.02 arcsecond. So they are going to be able to do better than that and just directly detect planets around stars. So it's a very, very promising experiment and very difficult to do. And the idea would be to block the light. So you mask out the light coming from the star and look for the planet directly. And they're scheduled to be launched between 2015 and 2020. So lots of things are expecting from that. Hopefully we'll be able to detect lots of Earth-like planets and many other solar systems. We'd like to detect solar systems that's similar to ours to confirm that actually it exists. We are not an exception. And start doing statistics, because now we have detected few of them. But what we want to know if our scenario is working. And for that, we need to have a large sample, unbiased sample of planets to be able to really see if the scenario of formation of planets is working very well. And there are particular things that we are interested in. And this comes out to this notion of what we call habitable zone. What we think is that to look for life, we need to look for water. Liquid water, actually. Because we don't have any knowledge of any form of life that can live without the existence of liquid water. We know things that are living without the existence of direct contact to the sunlight, or oxygen, or living in very high temperature, or in very low temperature. But so far, liquid water is the only requirement for life to exist, at least on Earth. So that's the first thing we're trying to look for. Things that are similar to Earth. So we're looking for Earth-like planets where liquid water can exist. So life could very well exist around other stars if the stars is old enough. Of course, you can't have life forming around all stars because they are living a very short life. Remember, life of the Earth is 4.5 billion years old, and life appeared very soon after, actually, 3 billion years old, or what? So we need a long time for life to settle. So if you look at a star that is very young and will die very soon, you won't have time for life to really start. So you need a star that is old enough. So, well, that means that we have to kick it away from the picture or be a stars, for instance. So we remain with the F, J, and M-type stars, for instance. We need to have an orbit of the planets stable as well. And then you need to have at least one planet living in habitable zone. So you need to have, disjoining that, is that you need to observe a system that is quite stable, that is look like the same for long enough. If planets still to shift around and kicked around, you will have no life appearing. And what we think is we need to have one planet living in what we call the habitable zone. That means not too close from the star. Sorry, if the planet is too close from the star, then this will be too hot, so you won't have a stable atmosphere and you don't have liquid water. But if the planet is too far away, then it will be too cold, and you won't have liquid water neither. So there is a zone for appropriate distance from the star for liquid water to be able to exist. So this zone we call the habitable zone. And of course, the bigger the star is, the further away this zone is, and the broader it is. So for instance, for M star, you don't have much choice. If you want to look for a planet around an M-type star that can host life, it has to be very close and a very narrow range. But even if we're doing that, we are selecting F, J, and M star. Remember, they are the most common stars. So billions of stars could actually have planets or moon with life on it. So if we look at habitable zone for different stars, from half of the mass of the Sun to twice the mass of the Sun, and this is the distance radius of orbit relative to Earth. So Earth is here 1, okay? 1 times the mass of the Sun and 1 astronomical unit. So obviously, Earth is on the habitable zone. As you can see on that picture, no Mars nor Venus are really in the habitable zone. And we know that when we describe Mars and Venus, actually the evolution make that even on Mars there were some water eventually, and probably in Venus as well, the water disappeared due to a greenhouse effect. Greenhouse effect for Venus and reverse greenhouse effect for Mars. So they are probably not in the habitable zone. And when you go for lower mass object, the habitable zone is closer, and bigger mass object, the habitable zone is further. So amongst all those exoplanets detected so far, are any of them within the habitable zone? So here, this example of 4 different planets. Their star is here. So some of them are multi-planet systems, like UPSENT. There are 3 planets in there. And this is the distance in astronomical units compared to parent star. And the gray area represents where the habitable zone is. So you see, for instance, this one is too close, this one is too far. And Gliss 8076 is a good example. The planet is within the habitable zone. So we may find liquid life on this planet, liquid water on this planet, or any form of life. Maybe eventually this one will work, also it's a bit at the edge of it. But we have example of planets within the habitable zone. Unfortunately, this planet, for instance, is a giant gas, so it won't be able to live on the surface of it. Life won't be able to develop on the surface of it. However, we could think that life could develop around the moon of it. So, however, this is not the end of the picture, because we are really well known that there are exceptions to the habitable zone. If there is any source of energy other than the sun to keep a planet or moon warm, then life can develop without seeing the sun. I told you, within the solar system we have good hope to find bacterial form of life in the icy moons of Jupiter. Europa mentioned, Ganymede, several of the icy moons of Jupiter may host life. The reason why is because even though the surface is very cold, when you go within the center of the planet, you may have liquid water. So possible energy sources: radioactivity. Remember, this is the way the center of the Earth is heated up. So radioactivity can be quite a strong source of energy, but actually tide effects are more likely. So remember Io around Jupiter that is constantly active and ejecting magma. It's not radioactivity that is keeping it warm at the center, it's actually the tidal effects that is constantly deforming these planets, this satellite. So you can imagine that, for instance, you look at Europa, I mentioned already several times, it's most likely could host life actually. So for instance, what you can think is, or there are 2 scenarios, right? Or we know that because those moons present a density slightly higher than the density of water, we probably have a metallic core in it, and probably rocky interior. But we know by observation that it's covered by ice. So there are 2 possible scenarios. Or you have a cold crust of ice, and below warmer convecting ice, or we can even have directly water, liquid water. And we know that, for instance, on Earth, there are some bacteria that are developing under a very thick layer of ice in the northern pole. So under the Arctic. Other moons like Titan have been ruled out due to a visit of different probes like Huygens. So we send a probe on it, and obviously we don't have trace of liquid water. But there is this interesting idea of experiments to send a probe directly on this planet and actually drill into it to try to reach the layer of liquid ice. And actually, last month, the European Space Agency, ESA, have agreed for the next generation of instruments, a facility that will be launched within the next 10 years. And the top on the list is called JUICE. It's called Jupiter Icy Moons. So it's an experiment that will go and monitor all the icy moons of Jupiter to detect presence of liquid water. So they will monitor from orbit around it, but they also send probe on the surface of it, and eventually try to detect the presence of liquid water on it. So we have good hope to find liquid water within the solar system, and maybe presence of very simple life. So you can imagine that around other exoplanets, maybe outside the habitable zone, we may also have conditions gathered to have life forming anywhere else. So it came down to the question is, what is life? So what we know is that to have life, you need life to be able to reproduce itself. and life to be able to adapt and pass changes to the new generation. So on Earth, we know that it requires a sort of genetic code. So this is an example of our DNA, human DNA. So we know that the DNA of any life form on Earth contains the genetic information, and this genetic information is able to replicate, transfer the properties of our living on Earth. Actually, people are starting to play with genetic using computers. So I don't know if there are computer scientists here, but it starts to be quite interesting. It's a coded genetic or numerical genetic, and we're trying to have create life forms that are evolved within the computer. So you probably have seen those games. They're very simple ones where Tamagotchi. It was things that I was a kid. It was coming from Japan. When you have a little egg it's a computer game. You have a little egg and it's growing, and you have to feed him, and clean his cage, etc. But you start to have a very, very complex version of it with genetic algorithms, and you can breed different species and create a full and adapt them, see them adapting compared to different conditions, etc., etc. So life, what's important with life is the fact that it may be able to adapt. If life can't adapt, then it won't survive. So this is the Darwinist push to the extreme. And actually, talking about that, there are some organisms that really can survive in extremely extreme conditions. In extreme conditions. So you probably know this story of the smokers. So those things are actually volcanic activity. It's just magma coming out in the bottom of the sea. So those things are 2,000 or 3,000 meters under the level of water. The heat around it is extremely high. It's around 50 or 70 Celsius degree. Remember, you are 2,000 meters on the sea bottom. Pressure is very high. It's emitting lots of sulfurs, etc. So those smokers are not very nice place where to develop life. However, we have detected many organisms, small organisms, living organisms around those things. And they were born there and developed there. So it's pretty harsh conditions. So what you need is a source of nutrients. So here actually those life forms are developing using the sulfates spread by the smokers. You need an energy of source. Here is the heat coming from the magma. And you need liquid water. Well, here you have many water. It's on the bottom of the ocean. We know existence of other form of life, for instance, within the rocks. So they are developing and living within rocks under the earth. So they don't have access directly to life. They use silicates as nutriments. So there are many different forms of life that are what we call extremophiles. And all those forms of life can develop in places where we couldn't think about even 10 years ago. And we keep discovering new forms of life all the time. So how could we potentially directly detect life around other planets? That's a good question. Well, the best way we can do with images is to possibly spot oceans, for instance. So you look at the color of the planet and try to detect presence of liquid of vapor water directly. But spectroscopy, once again, is a better way of doing it. So a better method is detecting life directly to look at the composition of the atmosphere. So if we have the case of a planet with an atmosphere, and it's a star here, and we're here observing, but this is this diagram here. So what you can have is that when we have this configuration, that means the planet is between us and the star, you will have light going through its atmosphere, and you will be able to detect absorption lines corresponding, for instance, here to the existence of water or CO2 on the surface of it, or methane. Methane is one of the best tracer of life on Earth. So you can, if you detect O2, for instance, or O3, or ozone 3, it's a good tracer as well. So this is typically the kind of spectrum you will look, absorption factor, you will look if you have this kind of configuration. So far, nothing detected. The other question is, how rare are Earth-like planets? So the location in your galaxy could potentially be important as well. We'll discuss about galaxy next week. But this is a sketch of our galaxy. So we discuss about that in more details probably during the visit at the museum and next week. And this is where the sun is. So the center of the galaxy is here and the sun is over there. Okay. And actually, we think that if you live too close from the center of the galaxy, you probably won't be able to develop life neither. So I don't want to come too much into details, but there are places around our galaxy that are not very nice where to live, especially spiral arms, for instance, because in spiral arms you're forming plenty of new stars, big obese stars, and you have lots of supernova explosion, so it's not really a nice place where to develop life. You need also to have Jovian planets to be at the right location and not move away from it. I mentioned that. If Jupiter had moved toward the center, Earth won't be there anymore. And on the size of the planet itself, if you want to see life appearing on it, you need probably some tectonic or some sort of geological activity, mainly because it's generating magnetic field that's protecting from solar winds and relativistic particles coming from the sun. And large moon is a must-have as well, protecting us from collisions. It's like a shield as well. So you need very, very peculiar circumstances for life to develop the way it develops on Earth. But once again, remember, there are billions of stars around there. So the chances that there is another one like Earth is pretty high. And just to finish, we have 5 minutes. I would like to finish with something that I like very much. It's the cosmic calendar from Carl Sagan's. So Carl Sagan was an American astronomer. If you're really interested in astronomy, you should read Cosmos from Carl Sagan, just explaining the formation of the universe. It's very simple, Cosmos, and it's very well written. So he's a very popular astronomer in the US, and they did lots of outreach, talking to public, making TV shows. And he came up with this idea, is to summarize the history of our whole universe in a year. So what he's doing is that he's saying that the 1st of January at midnight past 1 second is when the start of the universe happened, the Big Bang. We'll talk about that in 2 weeks, in details. And the 31st December at just before midnight, it's today. And it's describing how the different things happen within this time scale that talks to us better than billions of years. When I talk about 12 billion of years, it doesn't really hit your brain. But if I talk about days and months, then you will start to understand better. So let's set up the Big Bang, I mean the start of our universe, at a fraction of a second after midnight. Then, to see the first stars and galaxies appearing, you have to wait for March. And to see the formation of our sun and the planets around it, you will have to wait for August. Okay? So you have to wait 8 months. And the first non-life, like single cell, extremely simple life, you have to wait for September. So 9 months. And to have the first multicellular life appearing, it will happen somewhere in November. So you're already 11 months after. Okay? And now let's focus on December. So remember, in November, you have the first multicellular life. Around the 15th of December, you start to have what we call the Cambrian explosion. It's a burst of new life form. I can't remember the dates now, but a long time ago, we had a period on Earth when we have lots of life form that started to appear and disappear almost immediately because they were not able to survive. 17th of December, you have the first vertebrates that appears, and 18th of December, the first plants on lands. Okay. The first animal with 4 legs appear around the 21st, insects start to appear as well. 24th of December, the first dinosaurs. On Christmas, the first mammals appears. Okay, 27th, the first birds. 29th, so 5 days after, probably there is the heat of impact of the asteroids on the Yucatan that make the dinosaurs disappear. And then let's focus on the last day of the year, 31st December. At 10 a.m., the appearance of the EPS. At 9:24 p.m., so in the evening, you have the first human ancestor to walk upright. Then at 11:54 p.m., so 6 minutes before midnight, you have the first modern humans to appear. 15 seconds before midnight, you have the invention of writing. 10 seconds, the Egyptians' pyramids are built. And 1 second before midnight, you have the trip of Christopher Columbus. So just to put you back in the perspective of the scale of the universe. From the 1st of January, to see the men appearing, you need basically to wait for the last day in the evening. So I like this representation. It put people back in perspectives. Okay, so this is it for today. Do you have any questions?
You say the 4 larger planets is more easy to be find, right? But in the picture, most of them are about the size of Jupiter, right?
Below the size of Jupiter. The question is, on that picture, what I said is that it's easier to detect the biggest planet, but for the 171st planet detected, a large fraction of them were actually smaller than twice the mass of Jupiter. Yes, this is true. But remember that bigger planets are more rare, because you need to have more mass created around it. So those objects would be actually very rare. Those objects are more common. So the first object to be detected, and here you have another dimension that is not plotted, is how distant they are from their star. What is easy to detect is a big planet closer to the star. Okay? So the main part of the first planet detected were in this range between 2 and 5 times the Jupiter. Actually, 0.5 and 5. Okay? But because they are very close. And those very big ones were expected to be quite rare, because remember that the range of stars around which planets can be formed is very, very narrow. You can't form planets around very, very big stars. So the amount of material available for a planet to form is limited. So we don't expect to have extremely massive planets. And remember also that in this range here, fusion may start, and you may have a star formed. When you go to 15, 20, 100 times Jupiter masses, there won't be planets anymore, there will be stars.